So welcome to day 3, the last day of the conference. Looks like most of you made it back from the evening event last night, so great. I hope you enjoyed yourself. I have to give a lot of compliments to Hussein and Helen for getting that put together, because that was an amazing place. I thought the food was great. I thought everything about it just was well done. So congratulations. You know, we always, one of the things about the Swiss conference is we always have this Tuesday evening event. It's great. You know, we've been on boats here on the lake. Those have been fun. You know, depending on the waves, we've been up on the mountain. So every destination's always been an experience, but I think last night was just top. So thank you. I hope you all enjoyed yourself. We're going to do things not really a little different, but you know, at this conference we've given extended breaks. We wanted to do 30 minutes because we thought it was really important for everyone to be able to have time to have conversations and network, because that's kind of what this conference is really about. Yes, it's the material, but it's about being able to gather all of you in one place and be able to have those great conversations. So we're going to do a little test today and see, maybe at 40 minutes, how does a 40-minute break sound to everyone? Because even at 30, I'm pulling you back in here. So we're going to see what 40 looks like, and that'll be our first break. I want to say it was intentional, but it's not. So enjoy those 40 minutes.
Yeah, it would be great to have 40 minutes, but we're going to ask the coffee and to stop giving food and coffee exactly at 40 minutes. Sounds like having coffee always, that's really making it longer and people are enjoying it.
Hussein wanted to actually have the staff take it from your hands. I've convinced him that no. But yeah, no, it's great. I'm glad we're having these extended breaks. So enjoy. So we're going to start it off, and I'm going to let Hussein do the introduction here to one of our most esteemed colleagues.
So yesterday we talked about this flow of all our. We covered how this HPC advisory started, you know, giving some engineering task training, and then we start growing application to research, and then we just welcomed Taras, and it was really great honor also. But you know, in the third day we always would love to have always, like, you know, what we call the cream of the cream, and this is really Professor Torsten. That really we cannot miss it. This event is always looking for him, and what recently we have seen in the last achievement, direct achievement that Torsten got, and this is the ACM. This is well recognized prize that he got recently, and this is really an honor again to have Torsten here. First, I would like that you join me to congratulate Torsten for his achievements. So. And yeah, looking for the next achievement, Torsten. Stage is yours.
Okay, thank you. So no, thank you for setting so low expectations. That's always good. So I can. Exactly, that's going to be the first test. And Brian was complaining about that the whole last night, basically. This is not going to work, this is not going to work, and I'm going to prove you wrong. Look at that, perfect. Okay, cool. So yeah, my name is Torsten. Thank you very much, Hussein. And I'm going to talk about today something not so completely different, but I want to start with a little bit of a motivation here, because if you haven't been living in the cave for the last, let's say, 5 years, you probably know what's going on in terms of AI, in terms of revolutions, in terms of the stock market the last week, but I'm not going to talk about the stock market. But all of these things are quite interesting. And talking about caves, I actually want to start a little bit earlier and reflect on what we have been working on as humans for the last, let's say, let's say a million years. So it's going to be a long talk, right? It's slide 1 out of 200. So let's start in the Stone Age. What we have done, we have learned how to use materials. Actually, yes, I'm not going to talk about this. So Bronze Iron Age, we have actually developed quite a bit in the past. But what we developed more recently than that time is we developed technology. We developed medieval technology, Renaissance technology, and eventually the Industrial Revolution. And why do I talk about this? Because I want us to reflect on what may be coming next. That's, of course, the past. But what happened at the end of the Industrial Revolution is something that's a very deep change in human interaction, human society, human beings, because human physical strength stopped being relevant at the end of the Industrial Revolution. We all can use machines that are hundreds, thousands, tens of thousands, hundreds of thousands of times stronger than we are. Like, think about operating a big cargo ship. And a single human can operate this. So basically our strength is irrelevant. Was shown in many unfortunate events like warfare changed and many of these things. So now let's go forward. Like, since then, of course, technology continued developing. We don't stop as a humanity. Actually, we always accelerate. We went through the atomic age, the space age, the digital revolution. This is where I entered the planet. Well, slightly before that. okay, it looks like. Then we entered the information age, which is basically we digitalized things. Then in the information age, we connected all of us. We came up with the internet. We all had this information now accessible to essentially everybody. And now people believe we are in the data age, where we basically have access to all of that data that we have created with the digital revolution and shared through the internet. And now we have a gigantic corpus, which is essentially what many people say was part of launching the AI revolution. Like, we had all this data. Well, then one question you could ask is, when will human creativity and intelligence become irrelevant, be replaced by that data corpus? Right? This is what many people think about right now. This is not a question I'm going to answer in this talk, because the talk isn't going to be on Ultra Ethernet and we are a networking forum. I just want us to reflect on this, what that means, in what context we live. But I also want to stipulate that actually, I personally believe we are not in the data age anymore. We used to be in the data age. But we are now either entering or already in the age of computation. And let me make an argument for this. So many of us know this company, may have something to do with this event here. And now if you look at this company, it's quite astonishing. Well, it used to be number 1 for like a week, then it was number 2, and now it's number 3 because the stock market. But what's remaining is it's the fastest growth in human history, actually. It's a quite astonishing company. And the funny thing about this company is it doesn't make any data product. Like, this company builds compute accelerators mainly, and networks to connect them, but it's more like an afterthought, I'm sorry. So it builds mostly fast computing machines. And so that's one evidence that we are actually living in the age of computation already. We could go through more evidence. I don't want to spend too much time, but Sam Altman said last year, 1 year ago, that essentially the spoken language of all humans is only a factor of 1,000 more than the generated language of AI models. That was 1 year ago. Since then, we had probably exponential growth. So probably today, we generate more text or more speech with AI models than humans do. And there's much more. We run out of data. Synthetic data is great. Synthetic data could be better. But one interesting thing is that now there's a new movement. And you've heard one of my lab members yesterday talk about things like this. We actually want to really replace scientists. So what's a scientist? Actually, that's a very interesting discussion, what a scientist actually is. And I want to go back to my native language, which is German, so some of you understand this language. In my native language, if you translate scientist, it translates to Wissenschaftler, or science means Wissenschaft, which literally translates back to English, if we would, as create knowledge. That's what it means. So a scientist, by definition, creates new knowledge. So it cannot be knowledge that is in the data corpus that we already have. If it was on the internet, you wouldn't be doing science as a scientist. So you invent new things. So how can we now get AI models to invent new things? Well, we have to get them to hallucinate. Right? Many people think it's a bad idea. I believe it's a good idea if you control it. Because I, as a scientist, I am a scientist. When I come up with a new idea, I hallucinate a new idea, which many people call it educated guess or intuition, and then I prove that idea correct. Can we do this with language models as well? The answer is more or less yes. You've seen a talk on this yesterday by one of my lab members, Matcha. He's great, but I don't want to talk about this because I agreed with him to not overlap too much. But what I want to make the point here is that computation is what underlies all of these processes. If you look at graph of thoughts, if you look at chain of thoughts, if you look at any AI model or inference, it's all about computation. And I'm claiming now that as we are in the age of computation, computation is the new oil. The good news for a little country like ours here in Switzerland is we now have oil in Switzerland. Because Anybody can have oil at this point. And this is where Jensen walks around and gives his speech on sovereign AI and things like this. But this is really an opportunity that we are taking here in Switzerland. But I want to invite all of you to join us and take that opportunity moving forward, making a big change. So now the question is, how do we enable that age of computation? Well, the unfortunate thing is we need more and more energy. But there is an interesting point to be made about this. So most people say, well, it's kind of a negative part of what we are doing. Amazon buys nuclear power plants, and yeah, I know in Germany nuclear power plants are not that popular. But there's more nuclear power because it's actually one of the safer, not safer, but one of the cleaner options to generate power. And there is an interesting correlation you could make. If you look at the energy per capita, so let me actually get... If you look at the energy consumption per capita and the GDP, you see that there's a very strong correlation. It's not clear if the GDP comes from the energy consumption or if the energy consumption comes from the GDP. However, they're strongly correlated. So there's no low GDP country with a high energy consumption, or nearly no, and there's nearly no high GDP country with a low energy consumption. Right? That's the fact. Furthermore, if you look at the Human Development Index, there's a similar correlation. So somehow energy, the amount of energy humans generate in a society has a correlation with their development. There's even a Kardashev scale, it's called, where a scientist classifies alien life forms, I'm not kidding, alien life forms, so extraterrestrial life forms, by their energy use. Right? So it's a very interesting Wikipedia article. So somehow as a corollary, I would stipulate that we need to worry about optimized computations. And this is where we are getting closer to what I'm actually going to talk about in a couple of minutes. So now, what are we doing here? Well, we mostly engage in cloud computing. I wrote an article a couple of months ago, which we call ZAS. Don't want to go into too much detail, but the idea is that we want to push acceleration to be the most important thing in cloud computing, which it's not today. Today, usability and the business model is the most important piece in cloud computing. But actually, what we can learn from a community like the high-performance community, like our community, is that high-performance computing is now incredibly important. Right? We've seen it. One of the most recent Turing Awards went to Jack Dongarra. So he's the lead in the high-performance community. So that just reflects on how important the high-performance community is getting. So what we should keep in mind is that high performance should come first in the future, because computation is most important. We cannot afford to give up too much computational efficiency for anything else at this point because it is too important. However, we also want the benefits from cloud computing. We also want their view, which is ecosystem and market first. So we want to merge those into one business model, essentially. And the business model is somehow, I would translate this, as on-demand, high-performance cloud computing with longer-running jobs. It's a very mundane thing. But we hope to enable this business model with something we call ZaaS, Acceleration as a Service containers, where we package software in cloud containers, but we enable high performance for these cloud containers, which has not been the priority so far. Again, this talk's going to be on Ultra Ethernet. We're still in the motivation phase, so I'm going to move a little bit faster to get to the point. But in some sense, this high-performance new merge is going to involve both commercial cloud providers on the left and HPC providers on the right. So we have to move forward together. And we have to find standard portable interfaces to move seamlessly between those interfaces. Like, we at CSCS here are actually pushing this forward. So we are very much trying to spearhead that effort. And you'll see the talk right after me giving you more technical details on this. I want to use this a little bit as a motivation. This is going to be a wonderful talk. But at the end, we have some kind of base operating system layer. And then we have an acceleration layer in the containers, which is quite important, which doesn't exist today. And then on top of this acceleration layer, you can actually build various simulation platforms, data service platforms, and other high-performance service platforms if you wanted to. And again, look it up online. I don't have enough time to go through details in the slide, but that's somewhat a vision that is quite nice in my view. But now, let's get a little bit more towards networking, because I promised you a networking talk with the title. Okay, so what are we doing here? So if you look at cloud architectures and HPC architectures, you can see a certain form of convergence. Here you see each row is a provider. We also have HPC providers at the bottom. So again, cloud providers top, HPC providers at the bottom. They're often called on-premise. And if you look at the CPU architectures, they're basically the same. Right? Actually look at the GPU architectures, they're basically the same. Everybody's cooking with water, NVIDIA GPUs or AMD GPUs, same architecture, same thing. Where they differ, and even the network bandwidth is basically the same. Where they differ is in the network technology. This is literally Wild West today. If you go and check out what people are using in terms of network technology for performance computing, it's Ethernet, various forms of Ethernet, InfiniBand, and there's Rocky, which is kind of Ethernet packets, InfiniBand packets strapped on top of Ethernet frames. There's all kinds of stuff. Right? This is a big mess. And this is a big mess for people deploying the software, people deploying the hardware, but also people using these interfaces, because you now need to understand whether you use sockets, whether you use libfabric, whether you use UCI, whether you use UCIX, whether you use InfiniBand verbs. Like, it's just a little bit of a mess. So now, a long time ago, we realized, some industry partners realized, well, we need to somehow fix this. Well, a long time ago here is actually 2022. So in computing time, that's an age ago, because it's moving so fast. So we somehow need to fix it. And we wrote it down. What would it mean to converge hyperscale data center networks and high-performance computing networks? Because at the end, as I just motivated, these hyperscale data center networks, they must be high performance, right? Because that's what's going to happen. We can now talk through all these points here. I don't want to go into too much detail, but basically, the message of this is that yes, we can converge those. We have to feel, I mean, there have to be some trade-offs, so somebody has to give in on both sides, as usual when you have an agreement, but yes, we can do it. So we can actually, in 2022, we somehow concluded that you could merge these two types of networks, high-performance computing and cloud computing networks. Okay, but now, let's go a little bit more technical in the workload classes. So what do we actually do in AI and HPC? So now, when I say AI and HPC, I want to make very, very sure that my personal conviction is that AI is an HPC workload. So it's all about high-performance computing, and AI is a workload in high-performance computing. However, most people see AI as so big and so impactful that you always mention it separately. You say AI and HPC, even though AI is HPC. So I will adhere to that piece as well. So now we can classify these applications, both AI and HPC, along two axes. So one is their bandwidth sensitivity, in terms of networking, of course. How much bandwidth do they need? Little or much, left to right? Then, of course, as we know, bandwidth is simply a matter of cost. Like, I can add more bandwidth by having more network cards. I just throw more money at it. I have more cables, and then I will get more. The second axis is harder. It's the latency sensitivity. So that's the speed, or the communication time going from A to B. There's, again, a high and a low. Unfortunately, latency is extremely hard to measure, for once. Or latency sensitivity is hard to measure, and extremely hard to improve, because somehow we have the speed of light. So the only way to improve it, fundamentally, is to bring elements closer together, so to build more highly integrated systems, as you can see in the latest architectures. I mean, the NVL architecture that NVIDIA is proposing, for example, is one of those integrated architectures. Now we could say if we have low bandwidth sensitivity and a high latency sensitivity, those could be graph computations, actually. Well, you could argue about this if you wanted, and I'm happy to argue this. But this is just one possible classification. If you have high latency sensitivity and high bandwidth sensitivity, those are somehow strong scaling HPC workloads, so the classical strong scaling. Many of those are weather and climate simulations, but also LLM inference is a somewhat latency sensitive problem. If you have high bandwidth sensitivity and low latency sensitivity, then we are in the area of weak scaling HPC workloads. So lots of work to do, very little critical path, and AI training. AI training is very insensitive to latency, actually. And then if you have low bandwidth sensitivity and low latency sensitivity, well, then you're basically working on massively parallel jobs where there's no communication anyway, or very little communication. So it's kind of boring, but it's a big business. So you may want to support those as well. So now the question is, how can I measure the latency sensitivity? It's pretty obvious how to measure bandwidth sensitivity. You just look at how much the application communicates, like how many megabytes per second it sends. The latency sensitivity is not so clear. Like, how do you even measure how it changes for an application? Here I wanted to tell you about an earlier work we published at Supercomputing last year, which is exactly measuring latency sensitivity. It's quite complicated. I only have one slide. I don't have enough time to explain in detail. There's a talk online on our webpage, on our YouTube channel, in case you want to know more details. It was impactful enough at Supercomputing that the student got the best student paper at the conference last year. But what do? Is we trace an MPI program. By the way, the student is Sean in my group. He's absolutely great. So what do? So we trace an MPI program. We get to an MPI trace, like we all know. Then we take this MPI program and we model it as an execution graph, basically. Then we take this execution graph and we transform it. And this is now the new thing. Everybody does execution graphs. But we transform it into a linear program. an idea developed together with Langwen, another student in my group. And then we can basically do all these analyses that I don't have enough time to explain, but one of those is latency sensitivity. Another one is bandwidth sensitivity, but as I mentioned, it's rather simple. So now, it turns out that for actual application, the latency sensitivity varies widely. So there is an application, and here what we are looking at is we're looking at the network latency. So as we increase the network latency, how much of the runtime is going to increase? So you will always see a plot that goes from the lower left to the bottom, to the top right. So we'll always get slower as we increase the latency. Of course, you cannot get faster, right? That makes sense. But now what we're plotting here is at what point does the latency sensitivity, for what latency does the application slow down? 1% in green, 2% in yellow, and 5% in red. So this basically means at an additional latency of 22 microseconds, this milk application will be 5% slower than without that 22 microseconds. That's what we call latency sensitivity. Now we could look at different applications. So milk, 22 microseconds is very little. Lulash can actually take 65 microseconds. And ICANN can take 600 microseconds. So a weak scaling application can take 600 microseconds. So latency sensitivity varies a lot from 22 for a 5% slowdown to 600 for a 5% slowdown. So that's quite nice. And that's a factor of 32 at the end. So now the question is, well, does this matter? Well, of course. Well, we have to see what the latency and bandwidth of real systems is. So let's look at some data. And again, this is data that's collected on cloud systems and on-prem systems by a former group member of mine, Daniela. So we have AWS, Azure, GCP, Oracle, Pitstein, the pre-Alps system, which is basically the same as the Alps system, and the Deep system. So what do we see? I don't want to go through too much through the data, but if we look at a standard front-end Ethernet front-end network in the cloud service provider, we see about 20 microsecond latency. Well, that would already be kind of a slowdown of 5% for Lulash. Right? For some other applications, it wouldn't be a slowdown. Not Lulash, I apologize, for milk. For other applications like ICANN, you wouldn't see any slowdown at that. And then, of course, if you look at the specialized networks down here, InfiniBand and whatnot, they're very, very fast. So they have very low latency. Now the question is, do we need this low latency? Well, maybe. We could also look at bandwidth. For the similar networks, we would see a similar discrepancy in bandwidth. And what we've always seen in these earlier studies is that it was always Ethernet versus some kind of specialized backend network. So it was always Ethernet versus InfiniBand or something like this, or Cray's, I apologize, HPE's Slingshot network, or previous versions of this. And then there was this wonderful newspaper article last year, actually 2 years ago. Luminaries argue for the interconnect we could have already had. It's quite a sad story. That was actually alluding to Ultra Ethernet, and I'm wondering about the luminaries. So that is an interesting question. So the Ethernet ecosystem, what is this even? Right? So we as high-performance computing people, we don't, at least I didn't understand the Ethernet ecosystem before I was confronted with it. So I want to tell you my surprise that came up when I learned about the Ethernet ecosystem from a wonderful person at Broadcom, Ram Vilaga, and he gave this very nice talk. So he actually has a statistic that Ethernet ships 600 million ports annually. That's an interesting market. It's actually a high-performance deployment process, because that is 20 ports per second. Like there are 20 ports per second deployed, Ethernet ports, and that was 2023. And I don't think it got less, right? So Ethernet is a market that is just of a size that's uncomparable to the HPC market, right? So the Ethernet market itself. But now the question is, what is Ethernet? And then unfortunately, Ethernet is not Ethernet. There's a lot of variation, as I mentioned. Many people think kind of TCP/IP when you use Ethernet. I mean, if you're using your cell phone here, you're actually sending Ethernet frames, believe it or not. This talk is streamed and recorded using Ethernet frames, so Ethernet is a very powerful protocol. And then there is RoCE, which is the other extreme, RDMA over converged Ethernet. And as I mentioned, what is RoCE really? Well, converged Ethernet is kind of funny. RDMA over it is even funnier. I mean, I would call that whole thing IB over Ethernet, because it's really InfiniBand over Ethernet, because it's literally you take an InfiniBand frame and strap it on top of an Ethernet frame. So you have twice as many headers now. Oh, great. But hey, it works. It works in practice. So now let's go a little bit more into detail on high-performance computing and AI networks. What are the requirements? I talked about latency and bandwidth sensitivity. That's one form of requirement. But there are many other requirements. So for example, if you look at HPC networking here, we usually need small message efficiency and high message rates. Right? So that's quite important. We usually need MPI tag matching. Right? There's a lot of work on MPI tag matching. And we usually need a very large number of connections, which is also a little bit annoying in many ways. If you know about InfiniBand connection caching, then I'm sorry, you shouldn't know about that, because it should not actually be a problem, but it is a problem for some applications. Then AI is quite different, actually. In AI, we need extreme bandwidth, extremely high bandwidth. We need no tags. We don't need in-order delivery. So it's very different from MPI tag matching, essentially. You can use similar techniques to do it, but it's still different. We only connect to a few endpoints in AI workloads, usually less than 1,000, so you rarely get to 10,000. And we have very, very regular patterns, pre-plannable patterns, I call them. Like you actually know what's going on before you launch your application. You can compute your schedule for most of these applications up front. And both of those, AI and HPC, are bulk synchronous applications, which is very different from standard Ethernet assumptions. Because in bulk synchronous applications, the last message, and very often in Ethernet terms that's called a flow, that finishes determines the absolute performance, because you always wait for the last to arrive. Right? That's a very different setup. So now we want to converge those HPC networks, what I call a mess, many different technologies, into a unified standard. And of course, it makes sense to converge it into an Ethernet-based standard because there is a huge vendor ecosystem. Actually, Ram Velaga says in its talks that the Ethernet ecosystem is so healthy because it is a battleground for vendors, because you have pluggable components. Because if you don't perform, I just replace you with somebody else in a second. This is why mega data center providers love Ethernet. They can minimize their risk. They just buy from whoever has the best product at the last moment, because they can plug it out within a week. Right? If you're signing up for a proprietary interconnect and things go wrong, you have a deep problem. As many of you, I see many of you smiling who are operating supercomputers. That is a huge problem. And yes, I've been in that boat, and I am in that boat actually currently even. Don't want to go into details here. But yes. So, but now you could argue there's this rocky thing that I mentioned earlier, RDMA over converged Ethernet. Isn't that good enough? That was actually an interesting discussion we had a long time internally in a mega data center provider who I'm helping. And we eventually decided, well, no, for multiple reasons, and we wrote a paper about it with many industry partners. That was 23, where we basically said, well, you know, Rocky is not enough. And I want to give you a little bit of an insight why we believe Rocky is not enough before we go into the details of Ultra Ethernet. That was one of the motivations for Ultra Ethernet, because we realized, well, at the mega data center scale, Rocky has certain issues. Wouldn't it be great to start with a clean sheet proposal and come up with a new standard that is embracing the Ethernet ecosystem, but also all the experience we have gained in high-performance computing networking, and put it together and move forward together as a converged community, right? For HPC and AI, of course. Many companies got together. It's all history now. I was representing Microsoft. I'm representing Microsoft. I'm one of the founding members, actually, one of the first people involved in that thing. We wrote a white paper on it if you want to look at it. Interesting. So let me go a little bit more into detail why RDMA at hyperscale has some issues. And we can argue each of those issues. I'm sure some of you will disagree to some of those. I had interesting discussions with many people about this, but let me just point them out. So first of all, PFC, priority flow control, is a form of lossless transport. So the idea is that a switch is not allowed to drop anything. In a standard Ethernet switch, in the good old days, the Ethernet switches, if the buffer was full, would just drop packets. Like if I have two streams coming in at full speed, going to one output port, of course you cannot satisfy it. You have to reduce the speed by 50% for each of those two streams, because the one output port has only one bandwidth of 1, and I'm getting input bandwidth of 2. The Ethernet switch would drop 50%. That was not possible for InfiniBand at the time, because they have the mechanism that's called go back N. And that did not work with go back N because it was designed a long time ago, nearly 30 years ago, in a world where the computing itself relative to the bandwidth was very little. So they could actually not invest too much smarts into congestion control algorithms on the NIC, or flow control algorithms on the NIC, or reliability handling on the NIC. Like at the time, it was a great decision, but that was 30 years ago. Now we have 30 years of Moore's law later. We had a speed up of more than 1 million in terms of compute, but we have only a speed up of about 1,000 in terms of bandwidth, if you look at the numbers. Right? So now we have much more compute. So PFC was a good idea. PFC is now not the best idea anymore, I would claim, because it leads to very large buffer sizes in the switches, because you need to cover the whole round trip time of the cable with buffering. Because basically what it does is if you send a message to the destination will tell you when the buffer is running full to stop, like flow control. And now you need as much buffering as the round trip is covered, because I'm already sending the data. It cannot drop the data on the floor at the destination, so it has to tell you early on to stop, which is 1 full round trip time. As the cables get longer, that round trip time goes longer. As the bandwidth goes higher of the network, that data that you need to store grows. Right? And here we have just some statistics. On a 100T switch, you have to have 60 megabyte of buffers per port, essentially. Right? So that's a lot, high performance buffer. Now you could go even larger. I go at planetary scale. So I want to connect more data centers with lossless transport, with PFC, with Rocky. So here, inside the cluster, it's all good. I have tens of megabytes of buffering. But if I go, or even within the data center, a longer distance, up to 1 kilometer, data center is getting big these days, or to the region, or globally, I will need gigabytes, if not tens of gigabytes of buffering. Actually, these large switches exist in some providers. They have extremely expensive switches that have gigabytes of HBM just to cover the round trip time of the cable. Like, that is not fun. Especially debugging those things is not fun. Okay. So then we have things like victim flows, congestion trees, that are caused by PFC. So let me go a little bit more into detail here. So if you have two streams, like a source to a target communication, which, where the target has 4 incoming flows, essentially, or 4 incoming messages. So now it's obvious that the target is only connected with 1 cable to R2, which is router 2. And now each of those gets 1/4 of the bandwidth, right? So if you're operating ideally, everybody gets 1/4 of the bandwidth of incoming. So now you should actually get 1/4 at the source, because as I mentioned, PFC is not dropping packets. It basically tells the previous cable to slow down to 1/4. It tells the whole cable. That's the problem. Because what's now happening, if there is another source, source 2, to a target 2, which could actually be sending at 2/3 of the bandwidth, because that cable here in the middle has a 2/3 capacity remaining. With PFC, it'll only send at 1/4 of the bandwidth, because you regulate the whole cable to the quarter. Right? So you have so-called victim flows. There are flows that are independent of the congestion, but they feel the congestion because of these issues with PFC. Okay, wonderful. Then there is another problem that's called go-back-N retransmission. You can see I'm going through a laundry list here somehow. I want to get you the whole list. Go-back-N retransmission is what I mentioned is a very simple reliability protocol. How does it work? Well, I'm sending packet 1, packet 2, packet 3, packet 4. InfiniBand is in order. Rocky is also in order transmission, which at the destination I'm now seeing packet 1, packet 2, packet 3, packet 4. If I'm seeing packet 7 now, I know that packet 5 was lost. Right? So somehow in the middle it was lost. Now you wonder, how can it be lost? Didn't I just say the switch is not allowed to discard it? Well, it can still be lost because of cosmic rays or some corruption on the cable or something like this. Like if the checksum does not check out, the switch is discarding the packet. It's not discarding it voluntarily, like in the good old Ethernet days, but it may still discard it. But this is an extremely rare event. So in InfiniBand, there's nearly no packet loss. I mean, cosmic rays are not that bad, unless you're in Los Alamos, but that's a different discussion. So that's nice, cool. That's why go-back-N is as inefficient as it is, because what does it do? It doesn't actually track the packets. It really does not track the packets in InfiniBand. What it does, if the destination sees packet 1, packet 2, packet 4, packet 6, it says, oh, wait, packet 5 is lost. It sends a NAC to the source, but the NAC didn't actually keep track of the packets. It just didn't know what was sent. It says packet 5 was lost. Then the source is like, oh, I see, go back N. And then it retransmits packet 5, packet 6, packet 7, packet 8, packet 9. even though maybe packet 6, 7, 8, and 9 have arrived at the destination, but doesn't matter, it's fully discarded, fully retransmitted. That's what go back N is. Because at the time it was a very good choice, because the probability of loss was extremely low, and the tracking logic you need for this is extremely trivial. I mean, you just need one counter. Okay, cool. And as I mentioned, 30 years ago, the compute per available bandwidth was very little, so they had to do something simple, right, for this tracking. Now we are 30 years later, we can do more stuff, and I'll get to that in a minute. Now, congestion control and co-located traffic, it's more complicated. People basically patch things up at the end. We could talk about header sizes. As I mentioned, there are kind of two types of headers. We don't really support smart stacks too much in Rocky. We have security issues. I know there are lots of patches, proprietary patches from companies. They're not compatible with any other company, and that's the big problem. Like if I'm buying an in-network compute solution, for example, from NVIDIA, I cannot use an in-network compute switch from Broadcom. Impossible. I cannot exchange those pieces, and that's of course a problem for the market, because if I am a market player, I want to be able to have components. I want to be able to replace a vendor, as I mentioned earlier. And then there are a ton of security issues, actually. We have many scientific papers on breaking Rocky in practice for security reasons. Then there's link level reliability, which is a bit of another interesting problem. If you look at the FAC decoding time, one interesting thing is the FAC latency. So what is FAC? Forward error correction. Forward error correction basically means that, oh well, at some point the cables got so fast, the transceivers got so high frequency and so little noise, so little noise margin, that they actually had to, they weren't reliably functioning by default, so they had to add erasure coding on top to just get the reliability needed by the Ethernet or any other specification. So it's forward error correction. I'm basically adding redundant data to my frames such that the destination can decode and correct errors on the wire. It's a relatively new thing. It is standard in Ethernet, in high-performance Ethernet today, and unfortunately it causes a huge additional latency. But what's the fun thing here? This latency has two pieces. One is collecting the data to calculate the FAC, right? Because you have to have a certain block of data. It's very similar to a RAID system. And then the other part is to actually calculate the FAC. So the green part is to collect the data. Now, of course, the green part goes down the higher my link bandwidth is, because I need less time. If I'm coming with 800 gigabit per second, I need very little time to collect, I think it was 5 kilobyte or something like this. I forgot the exact number, maybe 10 kilobyte. Take very little time to collect 10 kilobyte. However, the coding time is still the same, right? So as I'm going towards higher bandwidth networks, I will have a larger fraction of the FAC coding time. At 800G, it's about 82%. So that could also be a problem. And then this is a very sciencey thing here, so I'm not sure how deep into detail I want to go. One issue with the development of congestion control and load balancing algorithms is actually that the bandwidth delay product is going up. What does that mean, the bandwidth delay product? It's basically the amount of data I'm putting on the wire before I hear anything back about what that data did on my wire. Right? Because I'm sending, and only once it arrives at the destination and the control packet travels back to me, I know whether anything has been dropped. I know what the congestion information is in the network. Right? So now, if that bandwidth delay product goes up, for example, here in this typical front-end network, that's like 6 megabyte. I'm blindly sending 6 megabyte on the wire, and I do not know whether it's completely congested, whether my destination is even there. I don't know anything until the 6 megabyte have been sent, which means my control circuit to load balance and congestion control has an extremely long reaction time. And this is deadly for these kinds of things. And we do have some innovation there as well, but I don't want to go into too much detail. For HPC networks, by the way, bandwidth delay products are still relatively low because they have very low latency. Right? However, as you increase the bandwidth of HPC networks and AI networks, of course the bandwidth delay product goes up because you multiply bandwidth by delay, which is latency. So more bandwidth will get you more data on the wire. So these are all things, these are all issues that we point out in this paper and that we wanted to fix in Ultra Ethernet. So we basically set out to fix these issues in an open industry standard, and it's very, very important. It's a fully open standard. Today we have 10 steering companies, many other companies. This is the the chair's view of our meeting. So if you're familiar with the MPI forum, it's very similar to the MPI forum. There's more skin in the game for many people, so more heated discussions. I'm not on the picture because I'm taking the picture, because I'm one of the co-chairs of the Transport Working Group, together with my wonderful co-chair Karen Schramm from Broadcom. So she's absolutely amazing, and here are some other people who are involved in the leadership and the technical leadership. So it's a great organization. I can recommend you all join in case you have not already joined, because it seems like everybody has already joined. So it's more than 100 member companies at this point, and 1,300 individual participants. And that was a slide from weeks ago, so I'm sure that has changed till now. So it's a quickly growing ecosystem. So everybody's on board. NVIDIA, you can see here, and many, many, many other companies are helping us to develop that standard. But what is it now about? So here's this nice comparison. I talked about lossless operation in classical RDMA networks. Ultra Ethernet supports mainly lossy operation, but also lossless operation. But we mainly advocate lossy operation. In-order transport, I mentioned InfiniBand is strictly in order. Classic RDMA is strictly in order. Ultra Ethernet is fundamentally out of order. Everything, not everything, okay. Everything we can get away with is out of order. Like some flows you have to keep in order, so there are different transport modes. Proprietary congestion controls that are not compatible between vendors, we are basically replacing with an open, flexible congestion control, such that you can plug together different NICs. So I can take NIC from vendor A and NIC from vendor B, and they would talk together. I mean, it's a standard, right? So that's what you expect. Single path routing on the classical RDMA side, as I mentioned, we do per packet multipathing, so fundamentally out of order delivery. But every packet may take a different route through the network, which is very important if you have transient congestion. So you, even in a single message, the packets of the single message are going different paths, which is called packet spraying, and it's quite a nice thing. Then, as I mentioned, congestion state, Q-pair state is quite large in classical RDMA. So thrashing of NICs is a thing. Ultra Ethernet has a fully connectionless API. So there are ephemeral states that are called packet delivery contexts to just reliably deliver packets, but it's not a connection as we know it. And security is added as a first-class citizen from the very beginning. So really, from the ground up, it's designed with security in mind. And what do we have as use cases? Of course, the usual suspects: MPI, OpenSHMEM, CCL. I mean, star CCL in Ultra Ethernet lingo means any collective communication library, because there's so many. There's like Nickel, Eckel, Rickel, 1CCL, and many, many others. At some point, I counted about 40 different acronyms for CCLs. So what do we now do? If we want to support HPC and AI, and then of course at the application layer, we have to be fully compatible with MPI and all these CCLs, which we do through a libfabric interface. At the bottom, we want to be Ethernet. It's called Ultra Ethernet at the end. So it's fully compatible with Ethernet, the standard 100G lanes, 200G lanes, so nothing special. You can plug in your good old Ethernet cable and it'll totally work. Actually, you can plug in your really, really old Ethernet cable. It has very little requirements in terms of Ethernet. You can plug in your 1 gigabit Ethernet and it'll still run over it, which I wouldn't do. So the data link layer, as of Ethernet, if you're an expert in this area, has been extended with two mechanisms: credit-based flow control, which is a lossless transport, and link-level retry, which is a way to amend FEC, because FEC is a forward error correction. Link-level retry is somehow a backward error correction. So if a packet gets dropped on the link, you retry it at the link level and not end-to-end. This is very standard technique as well. It's now standardized fully. The IP layer is basically unchanged. The internet protocol, same thing, nothing changes, fully compatible. You can route all of these packets to the internet if you want. I wouldn't recommend it, but you totally can. So you don't need to deal with this complicated routing modes that InfiniBand had at some point for the WAN connections. Now, what's the big news here? I keep talking about compatibility. Well, the big news is the transport layer. Right, that's where, again, Karen and I are the chairs of the working group, and this is where everything changes. The complete replacement from ground up, very different from anything else. So we have a semantics layer which basically hooks to libfabric. Right? So there are new ways to address nodes, quite flexible addressing modes. We have send receive, RDMA, RMA operations like you would expect. We have a new kind of operation that's called deferrable send, specifically introduced for AI workloads. We have the packet layer, a packet delivery sublayer, which is the ephemeral context for establishing like little mini connections, I would call it, but I'm not allowed to call it connections, so let's call it packet delivery context. So we have zero RTT connection establishment, or pseudo connection establishment, many flexible ways to detect loss and whatnot. We do congestion management in the thing. I don't want to go too much into detail because I have detailed slides later. And then we have, as I mentioned, built in the security sublayer. Now you're wondering, why do others not have this built in? Well, others rely on external features like IPsec, for example. IPsec is an encapsulation mechanism where you're encapsulating connections. So this is how we break it, like the papers I showed you at the beginning. We break the encapsulation mechanism with a very clever mechanism. So now this is all hopefully fixed in Ultra Ethernet and many more. So let me now go through these layers relatively quickly to give you some more insights of what they actually mean. So the semantic sublayer. So the idea of the semantic sublayer is, as the name suggests, to give you a semantic abstraction that is as compatible as possible to your application. We don't actually want to change anything at that layer, of course. So it's compatible with libfabric. So if you have a libfabric application, you can run it without changes. That's the hope. Okay, so many MPI applications will simply just run, like without any changes. Then there are additional RDMA services, so you can actually use the lower level features to optimize things, to make things faster. So we have send receive and RMA write. They're libfabric through the libfabric interface accessible. And really the focus is on MPI and nickel, star CCL semantics. New feature is scalable addressing to millions of endpoints. So that's not existing in most of the protocols today, but we can do it. It's quite a complex scheme, but it's extremely flexible. And then we have these extensions like deferrable send, as I mentioned. Deferrable send is a protocol that you can fully implement in hardware, like 100% hardware offload for AI communication. You basically have no software interaction besides just launching the thing. You just say, I want to send a message, I want to receive a message. Everything else can happen in hardware. You can, of course, also implement it in software if you want. Then the traditional HPC rendezvous is also supported with a little bit less hardware offload capabilities. So again, there are these two different, I probably should say that, there are different profiles in Ultra Ethernet. So we basically differentiate the use cases. So we have 3 different profiles, and I'll get to that later, but I think it should be mentioned here. So there's one HPC use case, because I remember the slide at the beginning where I showed you the different requirements for HPC and AI. We had that discussion for months, and then we realized, well, maybe we don't want to build one interconnect for HPC and AI, but we have one interconnect for both, but they have profiles. And if you're a vendor and if you want to sell an AI interconnect, you can specialize to AI and still make it a compatible product with all the other things. And if you're an HPC vendor, you can specialize it to HPC and still make it a compatible product. This is why we have these 3 profiles. So one is called HPC, which is optimized for small messages, essentially exactly what I had in my HPC list there, optimized for small messages, high message rates, and things like this. Then there are 2 AI profiles. One is called AI base, and one is called AI full. AI base is basically the minimum profile you need in order to support these workloads. It does not have things like deferrable send, for example. So this is the minimum thing if you want to build a very slim NIC at minimum cost. May not get you the highest performance. Actually, I personally am not so sure about the performance of AI base, but we'll see how it forms in the market. And then we have the AI full protocol, which has the full support for AI. Everything we envision, including deferrable sends, and that is gives you the opportunity for an AI optimized. If I had much more time, I could give full tutorial time, I could give you exactly the difference between this HPC AI full and AI base, but the high level difference is HPC uses rendezvous, like the one you know from MPI. AI full uses deferrable sends, which is basically a hardware-enabled rendezvous, if you want to build a very slim, super fast, super high bandwidth NIC. And AI base, the rendezvous is happening in software. Right? So that's the difference. So that's about what I just mentioned, the 3 different profiles. Okay, then at the packet delivery subsystem, as I mentioned, we have dynamic connections, which is extremely cool. This is much of what Karen defined in her section, so it's wonderful. So the key here is that we have 0 startup time. So essentially, how does that work? If you establish a TCP connection, you go a round trip. Like you have a SYN, ACK, and a SYN, ACK, and then a connection established in ACK. So it's always a handshake. It's even called a handshake. In Ultra Ethernet, it goes like this. Like you send the first message immediately pops up the PDC, packet delivery context, at the destination. And it's fully transparent in some sense. So single digit microseconds, actually nanoseconds. You can do it if your hardware does it well. It all depends on the hardware quality at the end. I mean, you can also do it really slow if you're kind of silly vendor. But this is why we have the market, right? Silly vendors will not live long. Okay, so that of course comes at a cost. Of course, we have to carry the full connection establishment information in the initial packet, so there's slightly more headers. But this is like 4 bytes or something. It's probably 10 bytes, but it's not much. And then we have various delivery services. We have a mode, it's called ROD, Reliable Ordered Delivery, which is exactly equivalent to the good old InfiniBand modes, or the good old RoCE modes. Reliable Ordered Delivery. The unfortunate fact of ROD is it is reliable ordered delivery, which means you cannot do packet spraying, you cannot do multipathing, you're basically not better than the good old RoCE or InfiniBand. However, if you need that semantic, you can use it. I wouldn't need it. I wouldn't use it. The real mode that Ultra Ethernet uses, the fast mode, is reliable unordered delivery, where I now allow the network to spray the packets all over the place, multipathing, everything, load balancing, super cool stuff. Still reliable. It'll still guarantee you that the message arrives at the other side in hardware, right? Then there is a mode that's reliable unordered delivery for idempotent operations, which is a relaxed, reliable, unordered delivery. Basically, if I'm sending a write, I can deliver that write twice, right? Because it doesn't matter if I deliver it once or twice. It's an idempotent operation. Some use cases can take advantage of this and make the hardware significantly faster. Some of you I see smiling, you're probably thinking about 3-letter organizations in the United States that do graph computations that have exactly that use case. Yes, it's exactly that. So super fast for that use case. And then unordered, unreliable, which is basically like UDP frames, in case you need that. I don't know if anybody needs this, but it was easy to add, so we basically just like, okay, if you want to send unreliable frames, you can totally do that as well. Then we have shared receive queues, that's a standard feature, out-of-order packet delivery and arrival, and then, as I mentioned, ROD is basically the same protocol as the old backwards compatible to RoCE, which is good old go back N. It was actually pretty funny in the spec. We tried to make it better, and we removed it at all the improvements we added. We removed at the end because they were had all corner cases that didn't quite work. So it's really hard to optimize RoCE in the constraints it has. So quite nice. The nice thing, what I can do in Ultra Ethernet is I can drop the state any moment. I can drop a connection. It'll just reestablish it the next time a new packet arrives or a new message arrives. So it's quite flexible. I love that part. Congestion control, we're using only standard ECMP, equal cost multipathing, standard feature in any Ethernet switch. I mean, there's no problem. We only need ECMP and ECN, basically. So there's minimal requirements for Ethernet switches. We have 2 different schemes. We have a network signal-based congestion control, which is a fancy term for sender-based congestion control, which is what TCP/IP does, for example. Of course, we are not using TCP/IP. We are using an optimized scheme. That should be available in all Ultra Ethernet products. So if you put an Ultra Ethernet logo on your NIC, when you sell it, you must support that protocol. It can be disabled, though, because we have a second one that's called receiver congestion control or receiver controlled. Which is also a good idea. I could go much more into, I can actually give a 2-hour talk about congestion control, so let me limit this to 2 minutes. Receiver control is good when you have many incast connections to a receiver. Sender control is good if you have an oversubscribed network. That's the high-level picture. So you can make use of both, depending on your traffic pattern and your network topology. So this is why we offer both. Receiver control is optional to implement, so not every NIC will have that. But if you have it, you can actually turn off sender control if you really know what's going on in your network. So it's very, very flexible. So essentially, you can support a ton of use cases on HPC and AI and all together with multipathing. So I could say a little bit more about congestion control. It's an algorithm that we developed with many partners. You can see here, I mean, multi-institutional thing like Microsoft, universities, AMD, and yeah, that's basically it. Broadcom, sorry, yes, exactly, Broadcom. So multi-institutional development. We got together, develop it. We could talk about the performance now. Again, I don't have time. He's already showing me numbers here. It's a relatively simple algorithm. It's only 37 lines of pseudocode. We have a lot of data that supports that it runs, and that's basically very similar to the algorithm that we adopted in Ultra Ethernet. There are some minor tweaks to it, but that's the algorithm. So transport security, which, as I mentioned, it's a built-in feature. It's really, really nice because built-in end-to-end AES encryption and specified key derivation protocols. We actually do derive keys on a per-peer basis, which makes it extremely secure in my view. Of course, you never know because security is always a game of probabilities. How high is the probability that you're being taken over? It is extremely scalable. As I mentioned, the whole thing scales to millions of endpoints. So the whole security solution also scales to millions of endpoints, which means you're not going to have a million keys at any of these endpoints, right? This is quite nice. Many standard features are used. So we learned from IPsec, we learned from PSP. We fix all the attacks that my group has published on RDMA, basically, so they don't apply. I'm sure there will be new attacks, because that's how security works. So I'm sure some of my smart future students will figure out how to break this thing, but we'll see. Maybe not, hopefully not. And it's extremely high scalability, like group rekeying, secure domains, very strong isolation properties. So that's basically it. I want to summarize again. So Ultra Ethernet is coming. Very soon, we will hopefully have a spec publicly available, and there will actually be a meeting next month where we hopefully converge on things. It's growing quickly. If you're interested in this, I can recommend you join. It's an open forum. Anybody can join. There's a certain fee associated with it, but well, if you're a company, you can do that. And then I talked about some technical features. Not too much in the technical detail, because that's all we can release at this point. The spec will be released in its full glory, hopefully very, very soon. I'm hoping 2 or 3 months, but I shouldn't say that. And if you're interested in research in this area, I'm running a research group at ETH Zurich, where we are always welcoming visitors, academics, and people talking about these cool things. Thank you very much, and I think there's even time for questions, if Brian allows.
Thank you, Torsten. Great presentation. And that UEC Member Summit is going to happen in Denver, April 28th through May 2nd. So
exactly.
If you want to check it out, I think it's a very easy website, or it's probably linked on the UEC website.
It's called the UEC Summit, exactly. It's
in collaboration with SNIA. So it's 2 events in 1. Okay, any questions for Torsten? Yes.
Hi, Torsten. Thank you very much for the really good presentation, and I'm agreeing with you with the key findings regarding ROCI and InfiniBand. I'm wondering, Hussein mentioned 16 years ago, the HPC AI Advisory Council was started to educate people on InfiniBand. So it's not a technical question. What does the industry needs to do to establish the ecosystem for this new standard in regards devices, switches, and. I mean, I understood the cables are the same,
yeah,
but the rest is clearly not the same. So how can we, from an industry point of view, help?
Oh, this is an excellent question. We have a lot of discussions about this, actually. It turns out that it's less of an educational lift as InfiniBand was, because of course all the cables in InfiniBand changed, all the management changed, the management frameworks. In this Ethernet thing, all of the layer 2 parts of layer 3 are exactly the same. Like layer 2 is exactly the same. If you like your switch management system, you can deploy, I don't know, Sonic, or I don't know what you want to run on this thing, open source switch management systems. Like you can use your old crummy Cisco software in case you're educated on that 20 years ago, will totally run. So that's a very easy lift up to layer 2, parts of layer 3, which is routing. So routing configuration is basically also the same as Ethernet, so not too much changes. It's all ECMP. Okay? But then you're looking at the higher levels where I mentioned transport is completely different. That's true. But transport, you only configure essentially the congestion control and load balancing algorithm, so there's a little bit of education necessary also for ourselves. I mean, we are very curious how this performs in the field, because we have only simulations at this point, right? So I'm very curious to see the first products to actually run stuff at high scale. Very important is that these algorithms that I couldn't talk about for time reasons, they have a gazillion, not a gazillion, but they have many knobs. So they have like 40 parameters or so you can set. And so this will be an interesting exercise to set these parameters. We hope they're easy to set, because in all of our simulations they were relatively easy to set, but we added more parameters just to make sure that if something goes wrong, we can correct. Right? So that's probably the biggest lift. We would need to configure congestion control load balancing. Also, congestion load balancing is interesting in this spec because it allows a wide variety of load balancing algorithms. So how they interact between different vendors is an uncharted territory. So we have no idea. Then at the top level, you just need to learn libfabric. And again, libfabric is an existing thing. There are tutorials online, many tutorials actually given by Intel and other people. So the top level, the bottom level is basically the same. It's only the transport where it's only load balancing and congestion control. There will be educational events, and I'm assuming, I don't know, we've got to look at Brian and Hussein here, that parts of this venue will be used to educate people on Ultra Ethernet as well. So that, I think that's going forward, yeah. The ecosystem, again, the lower thing exists, right? All these operating systems, the top thing exists. The middle is all vendor specific. So here is a good question now. Will these vendors get together and develop an open source ecosystem like we know, for example, from OpenSM as a configuration tool? But now, many vendors have proprietary versions of OpenSM or better versions, and I remember the Mellanox Gold edition, which was not quite, and it's the same today. We will see. This is not in the spec. The spec just says what the parameters you need to have. How you get them in there, totally up to them. Also security configuration, by the way. We do not specify how to establish a secure context. That is up to the vendors. And the main reason was that I'm helping one data center provider. There are many other data center providers involved. They all have their own way to roll keys and to deploy keys. So you want to give them the opportunity to not change their model. Right? And this is how it's going to be. And I'm assuming there will be an open source solution for all of those, if you want. Like OpenSM, there will be a thing like that, yeah.
I kind of want to expand on the ecosystem thing. In your viewpoint, because you're talking 3 different classes of the Ultra Ethernet spec that a vendor can comply to.
Yeah.
There's probably a handful of Ethernet switch vendors today with one having 90% market share.
Yes.
Dangerously close to proprietary.
Well, but this Ethernet, they offer Ethernet. I can plug them out versus a Huawei switch, for example.
Right. Right. Yes, I mean, there's many vendor switches based on a single silicon. Yeah. So, and the amount of NIC vendors is kind of small too. Maybe
very
2
true.
hands.
Yeah.
I would find that all those vendors, it'd be easy for them to hit that lower end of the spec, that classification. Do you anticipate an issue where you might have a single vendor only being able to be on the higher end, on the HPC end?
That may happen. I hope not. I hope not. Because if that happens, that would not help us much. You're right. You're talking now about the market. What is the market going to do? That is a good question. But what any mega data center provider will make sure is that there are at least 2 providers for a product. They will make sure the other one stays alive. I know that for sure. Because you cannot afford a single vendor only. There are also governments that will make sure that there are at least 2 providers. Like looking at the DOE, DOD. They will make sure there are 2 providers. And now the spec will just help them to do this, because right now the governments have or anybody has a very hard time to have 2 providers. It's an extremely hard sell. I cannot switch in the last moment. If I'm building El Capitan, I sign up for Slingshot. And if Slingshot doesn't work, I'm not saying it doesn't work, but if it doesn't work, you have a problem. Right? With Ultra Ethernet, you're just like, come on, AMD, get me a different one. Right? So,
right.
But there are many questions behind you, by the way.
Oh, you want to move away from me? Okay.
No, absolutely not.
I
absolutely.
so many no, I'm only kidding.
But I'm just saying that this is a market question that you're asking, not a standards question. I'm a standards guy.
No, I mean, I'm just thinking in terms of overall,
The very fun observation with that essentially single vendor ecosystem on the switch side is that any data center provider can immediately switch them out. Like they can, they just don't do it because this single vendor consistently gives us the best product. Right? And if that single vendor once makes a misstep, they may end up like another big vendor starting with I ending with an L. But that's an open ecosystem. If that vendor consistently delivers, it's good for me. I don't care. With InfiniBand, I don't have that option. I simply don't have that option, or with HPE. Yeah.
So, thank you very much for the talk. It was very interesting. You know, when we talk about libfabric and this looking upwards towards the communication protocols that go on top of that. So the CCLs, I mean, MPI is kind of one thing, but if we look at the CCLs, I would say their integration to like libfabric targets is not ideal. And there's, you know, again, we can talk about single vendor and whatnot. What has been your experience so far in conversations with this? Where's the community thinking? Are we going to see better integration with libfabric and optimization for that versus just say InfiniBand?
I can see a deeply hurt customer of Slingshot speaking here. Yes, I feel the pain. Yes, the ecosystem is not there. Absolutely. I mean, there's basically for everybody else. If you have to work on the fabric today with nickel or with a CCL, there's one plugin by AWS which is kind of like half maintained, and it's kind of like half working. So this will change because right now there's only one vendor that uses that, right? Imagine now the whole ecosystem will embrace this. So we are actually launching a software initiative to build this middleware for the future. So this will, not yet, but this will have to happen because otherwise the whole thing crumbles, right? If you don't have software that works. So there must be a software initiative, and this must be a neutral ground. This cannot be a single vendor-led software initiative because that is kind of silly, right? So it must be a consortium like MPI or so to contribute to this with multiple vendors and things like that. So like Open Fabric, basically, Open Fabrics, yeah.
Thanks for the perspective, especially thinking about your early chart. You had, oh, well, there's similarities in processors, similarities in accelerator, and so this is addressing, you know, multiple transport layers under the same. But how do you think that will impact topologies? Because there was also a high variance in topologies which won't really address.
I love that question. So in UE, we decided for now that is all optimized for fat trees. Okay. So the whole thing is tested, and because that is the major market. If you look at the deployment, it's 90+% of the ports deployed are deployed in some form of fat trees. Now as an HPC guy, as a person who has been working on topologies, it's very disappointing. So we are actually, as a research group, but also in collaboration with many companies, we are exploring now how to enable different topologies. And the early results, and I may give the talk here next year about UE for Dragonfly or something like this, very likely actually. Early results show absolutely this is possible with all the protocols we have. It's just that we want to get to market, and so we have to limit the options we certify. As a consortium, like large consortium. So there are splinter groups like mine who are spearheading different topologies. And I can say with minor, very, very minor modifications, Dragonfly is going to work fine, Slimfly is going to work fine, and all compatible. So yes, not officially, but yes. Very good question, by the way. There was a long discussion on this.
Last question.
So the talk, you mentioned about 3 different profiles in which the UE standard will operate. How would it work in practice for somebody like us? We have made a bulk purchase of a certain kind of compute node, certain kind of network, and we are carving vCluster platforms out of it. So will we be able to use the AI full protocol for the ML platform and the HPC protocol for the HPC platform? How would that work?
No, because you're going to buy a product that supports a subset of these. Or actually, it could support all of them. I could make a NIC that supports AI full, AI min, AI full, AI base, and AI and HPC. So you're going to buy a product. It's very unlikely that anybody would make such a product. So you would probably buy an either HPC NIC or some form of AI NIC. Like there are 2 different market segments. Oh, sorry. And if you're an HPC person, you have the HPC NIC. And then it does not necessarily talk to an AI NIC. It could. It could, but it's not guaranteed. I think so. And what vendors could also make is very interesting. They could, for example, build an AI base NIC with deferrable send. This is allowed. You could announce, or you could advertise this in your documentation, and then you could talk to various other things. So the specification is modularized. So you can basically even beyond these profiles, you can say I'm supporting feature X, Y, and Z, which is in another profile. The HPC profile is the biggest profile, so it's the heaviest to implement. It's basically everything but deferrable send. But if you want to implement all of UE, because deferrable send is for AI, you could also say, well, I implement HPC plus deferrable send, and then I basically have like the everything NIC. So that's all possible. But if you now buy a specific profile NIC, you have to, we say you have to decide at purchase time, right? What you buy. But then later you can, if you buy one that has a superset, you can reconfigure at runtime or at deployment time. Because it's different hardware.
Torsten, thank you. Fantastic talk.